This is lesson 29 in our Calculus 3 series, Sequences. A sequence is an ordered list of numbers with an infinite number of terms. So here we're calling our sequence A sub n, and we're numbering our terms A1, A2, A3, etc. For example, 0, 2, 4, 6, ... and the ... indicates that it's an infinite sequence. Another example, 1/3, 1/9, 1/27, ... We can see there's a pattern forming in each of these sequences, and we'll talk a little bit about that in another minute. Another example, 1, -1, 1, -1, ... The notation we have for sequences is that we either list the first few terms, enough terms so that we can recognize the pattern, or we find a formula for the nth term of the sequence and put that in the set notation brackets. And sometimes with that notation, we'll specify that n is going from 1 to infinity, or maybe it's going to start with a different number and go up to infinity. So let's talk about this notation where we find a formula for the nth term of the sequence. Let's do that for the examples above. Here we have n equals 1, here n equals 2, here n equals 3, here n equals 4. Now normally when we talk about the even numbers, the even integers, we think about 2 times n or 2 times k, but notice it's not exactly what we have here. When n is equal to 1, 2 times n would be 2 times 1, which would be 2. And then 2 times n here would be 4. And so we would have 2, 4, 6, but that's not exactly what we have. Notice here, for n equals 2, we have 2 times 1. Here, for n equals 3, we have 2 times 2. Here, for n equals 4, we have 2 times 3. And here we can consider this to be 2 times 0. So what we have is 2 times n minus 1. So we're going to say this sequence is equal to the sequence 2 times n minus 1. And if we wanted to be specific, that we're starting at 1 and going up to infinity, we could say 2 times n minus 1 and going from 1 to infinity. Now let's take a look at what we have for the second sequence. Here we have n equals 1, here n equals 2, here n equals 3. It looks like in each case we have 1 over 3 to the nth power. So this sequence we could write in set notation as just 1 over 3 to the n. And certainly if we wanted, we can put n equals 1 to infinity on this as well. Now let's take a look at this third sequence here. We have 1, -1, 1, -1, and it's going to continue to oscillate like that. Again, here we have n equals 1, n equals 2, n equals 3, and n equals 4. And I want you to consider here -1 taken to the nth power. What's going to happen here? When n is equal to 1, we're going to have -1. When n is equal to 2, we're going to have +1. When n is odd, we're going to have -1. When n is even, we're going to have +1. But that's not exactly what we have here, because here we want an odd n value to give us +1, and an even n value to give us a -1. That means for an odd n value, we need an even exponent. So how about we just add a 1 here? Now when n is odd, we have an even exponent, and this becomes +1. That's what we need. When n is even, this becomes an odd exponent, and we get -1. So that is the notation we're looking for. And you might not have seen this before, so you might not have thought of this on your own, and that's perfectly okay. But it is going to come up a lot, so you definitely want to remember this. Now let's take a look at finding a formula for the general term an of the sequence -1/2, 1/3, -1/4. Well, the first thing I notice here are the pluses and minuses. Now we just took a look at a formula that gave us oscillating plus and -1. So that is going to be part of the formula for an here. Now, do we need -1 to the n or to the n plus 1? Remember, this is n equals 1, n equals 2, n equals 3. For n equals 1, we want a negative sign. So in fact, we can just put an n here. When n is odd, we want that negative. So that's perfect, -1 to the n. When n is even, we don't have the negative, it becomes +1. So that's perfect. That's a starting factor for our formula for a sub n. But what else do we need? We notice that we're dividing here. For n equals 1, we're dividing by 2. For n equals 2, we're dividing by 3. For n equals 3, we're dividing by 4. So we are dividing here by n plus 1. And so this is the formula we're looking for. It says find a formula for the general term a sub n. There we go. That's a sub n for us. Let's take a look at another one. Again, this is n equals 1, n equals 2, n equals 3, n equals 4. Now let's see what we have here. The first thing I notice is that in our numerators, we have powers of 5. This is 5 to the first, 5 to the second, 5 to the third. Here, probably we're going to have 5 to the 0 then. But we have 5 to the first when n is 2, 5 squared when n is 3, 5 to the third when n is 4. So it looks like in our numerator we're going to have 5 to the n minus 1. And what's in our denominator? We have 2, 6, 24. We should start to recognize these as n factorial. 2 factorial is 2 times 1, that's 2. 3 factorial is 3 times 2 times 1, that's 6. 4 factorial, 4 times 3 times 2 times 1, that's 24. So we recognize that here we have n factorial. Now let's just check for n is equal to 1 if the same formula holds. 5 to the n minus 1, 5 to the 1 minus 1, that's 5 to the 0. That's going to give us a 1 in the numerator. And then 1 factorial is just equal to 1. So we have 1 over 1, and yes, that formula does work also for the first term of the sequence. So this is a sub n that we're looking for. Now it's often convenient to consider the function f of x for which f of n is equal to a sub n, where n are the positive integers starting at 1, or sometimes we start the sequence at 0. But you'll see that by the sequence definition. If we were starting at 0, we would put a note n equals 0 to infinity. So unless otherwise specified, you can assume that n starts at 1. So for example, the sequence we had above, 1/3, 1/9, 1/27, we said that we can write that as 1 over 3 to the n. So f of n is 1 over 3 to the n. What would that look like as a function of real numbers? F of x is 1 over 3 to the x. Because we're so used to studying functions of the real numbers, we're much more comfortable with f of x than we are with 1 over 3 to the n. So it's often convenient to talk about the function as if it was a function of the real numbers, even though we know the sequence elements are only what we get when we plug in these positive integers. So keep this in mind. We're going to use this in another minute or two. And also keep in mind that factorial only makes sense for integers, n greater than or equal to 0, and 0 factorial is 1. So if we had a factorial in our sequence, it really wouldn't make any sense to talk about the function as a function of real numbers. Now let's take a look at graphing sequences. For example, our sequence 1/3, 1/9, 1/27, 1 over 3 to the n looks like this. We have 1/3, 1/9, 1/27, 1/81, etc. And notice that we're plotting these points above the corresponding n value. And by looking at the graph, we could see that these sequence terms are approaching 0. Right? As n goes to infinity, 1 over 3 to the n is going to 0. We're going to talk about limits of sequences in just a couple minutes. Let's take a look at negative 1 to the n plus 1. Here we have when n equals 1, our sequence value is positive 1. n equals 2, our sequence value is negative 1. For n equals 3, positive 1, n equals 4, negative 1, we can see that this sequence is going to keep oscillating, and the values do not approach any limit. Another example from above, we had negative 1/2, positive 1/3, negative 1/4, positive 1/5. We can see that although the signs are oscillating, the positive and negative signs are oscillating, these points are getting closer and closer to 0. So it does look like negative 1 to the n over n plus 1 goes to 0 as n goes to infinity. Now let's talk about this idea of limits in a little more detail. The limit of a sequence. A sequence a sub n has the limit L, and we write limit as n goes to infinity, a sub n equals L, or we can just write an goes to L with an arrow. If, for all epsilon greater than 0, there exists an integer capital N such that n greater than capital N implies the distance between an and L is less than epsilon. This is saying however close you want to get to the limit L, pick any small number epsilon. However close you want to see your sequence get to that number L, we can find a capital N such that all the terms after a sub capital N are close as you wanted to L. We can find a capital N such that little n greater than big N implies that we get that inequality we're looking for. Now, if the limit exists and is a real number, we say that the sequence converges. Otherwise, the sequence diverges. We can also say the limit is equal to infinity if for all positive integers, capital M, there exists a capital N, another integer, such that n greater than capital N implies that an is greater than m. So this is saying however big you want the sequence terms to get, for all positive integers m, pick a big positive integer, however big you want the sequence terms to get, we can find a capital N such that all the terms after a sub capital N are as big as you wanted. Now here's where it comes in handy to use the function f of x when you're talking about your sequence. We have a theorem that says if limit as x goes to infinity f of x is equal to L, and the sequence is defined by f of n, a sub n is equal to f of n, for positive integers n, then limit n goes to infinity, a sub n is also equal to L. So for example, look at the sequence that we plotted before, 1 over 3 to the n. That's these individual points here, these dots, right? The function f of x equals 1 over 3 to the x is this curve. Now from what we know about exponential functions, we know that this limit is equal to 0. Now if we know this function approaches 0 as x goes towards infinity where x is any real number, then certainly the values at these individual points are also going to 0. So if we know limit x goes to infinity 1 over 3 to the x equals 0, then the limit n goes to infinity 1 over 3 to the n is equal to 0. And of course we know this limit from what we know about exponential functions. So we can say that 1 over 3 to the n converges to 0. Now let's talk about the tools we have for finding the limit of a sequence. The first tool we have is what we just saw, that if limit x goes to infinity, f of x is equal to L, then limit n goes to infinity, f of n is equal to L. And I want you to keep in mind that this can include using L'Hopital's rule to find the limit of f of x. Another tool we have is the properties of limits. if an and bn are convergent sequences and c is a constant, then the same rules for limits we had with functions all hold. All of these properties hold. We also have a version of the squeeze theorem for sequences. If the sequence Bn is between an and cn for all n greater than or equal to some n naught, and limit n goes to infinity an is the same as limit n goes to infinity cn, if that limit is L, well then Bn must also have L as a limit. In other words, if these terms are going to L and these terms are going to L and the Bn are always between them, then the Bn have to also be approaching L. And we're going to take a look at an example in just a minute. We have a theorem that says if the limit as n goes to infinity of the absolute value of an is equal to 0, then the limit as n goes to infinity of an is equal to 0. So remember that -1 to the n factor that we had to show an alternating sign? This is saying that we can consider the limit of our sequence without that alternating sign. And if that limit is equal to 0, well then our original limit is equal to 0 as well. We also know that the sequence r to the n is convergent if r is greater than -1 and less or equal to 1. And it's divergent for all other r values. And if r is strictly between -1 and 1, that sequence converges to 0. If r is equal to 1, that sequence converges to 1. And now let's take a look at some examples. For all of these examples, we want to find the limit as n goes to infinity of an if it exists. So let's take a look at this one, -1 to the n times n over e to the n. So when we look at this and we want to examine if the limit exists here, first thing we should do is get rid of the -1 to the n. Let's first examine n over e to the n and see what we can figure out about that. So we take a look at f of x equals x over e to the x. And let's think about this as a function and if the limit exists as x goes to infinity. Limit as x goes to infinity, x over e to the x. This would give us infinity over infinity. So we realize we can use L'Hopital's rule here. So that's limit x goes to infinity, the derivative of x is 1, derivative of e to the x is e to the x. And as x goes to infinity, we're going to have 1 over infinity, that goes to 0. So we know that the sequence n over e to the n also goes to 0. But what are we going to do about this -1 to the n? Well, we know that we have the theorem above that says if the absolute value of your sequence goes to 0, so does your original sequence. Putting absolute value bars around our original sequence gives us n over e to the n. We know that goes to 0, therefore the original one does as well. So we could say here that this sequence converges to 0. Let's take a look at another example. 2 times n plus 1 factorial over n factorial. So let's take a look at the limit as n goes to infinity of that term. Well, we know that n plus 1 factorial is going to be n plus 1 times n factorial. And then our n factorials cancel in the numerator and the denominator. So we're left with limit as n goes to infinity 2 times n plus 1. As n goes to infinity, this goes to infinity. So this sequence diverges. Remember we said that a sequence converges when the limit exists as a finite number, not infinity. So this sequence diverges. Now let's take a look at 4 to the -n. Now we're trying to use the tools that we talked about above, so I'm trying to get this to fit r to the n formula. So I'm going to first recognize this as 1 over 4 to the n, or 1/4 to the n. Now I have it in the proper form. R is equal to 1/4. Because r is strictly between -1 and 1, we know that the limit is equal to 0, and so this sequence converges to 0. Now let's take a look at a squeeze theorem application. The sequence sine n over n. Now I always think about the squeeze theorem whenever I have sine and cosine, because I know that sine and cosine values are bounded by -1 and 1. So often when we have a sine n or a cosine n, we could set up sequences an and cn around it that both go to the same limit. In this case, we start with -1 less or equal to sine n less or equal to 1, and we realize because the n values that we're talking about are all going to be positive, we can divide each of these terms by n and preserve the order of the inequalities. So we're here. So now we've got our sequence stuck in between two others, and notice that those other two sequences go to 0 as n goes to infinity. Well, if these values are always going to be in between -1 over n and 1 over n, well, these values must be going to 0 as well. And that's what the squeeze theorem says. The limit we're looking for is equal to 0. So this sequence converges to 0. Now let's talk about increasing, decreasing, monotonic, and bounded sequences. We say a sub n is increasing if an is less than an plus 1 for all n greater than or equal to 1. It's decreasing if the terms decrease, if an is bigger than an plus 1 for all n greater than or equal to 1. We call it monotonic if it's either increasing or decreasing. We say a sequence is bounded above if there is a number, if there exists an m such that a sub n is less or equal to m for all n greater than or equal to 1. So what this is saying is that all the terms in the sequence are all less or equal to this number. That means your sequence is bounded above. Similarly, we could talk about bounded below if there's a number so that all of your terms are greater than or equal to that number. And then if a sequence has a bound above and a bound below, we call it a bounded sequence. And then we have the monotonic sequence theorem that says if your sequence is bounded and monotonic, it must be convergent. In other words, if there's an upper bound and a lower bound, and it's always increasing, it must converge. Or if it's always decreasing, it must converge. So for example, let's take a look at 1 over n factorial. We know that 1 over n factorial is going to be bigger than 1 over n plus 1 factorial because remember, this number in the denominator is going to be bigger than this one, and that means that whole fraction is going to be smaller. So this inequality holds for all n greater than or equal to 1. So for the entire sequence, we have this inequality holding, and that says that our sequence is monotonically decreasing. Now, because we know this is monotonically decreasing, we know that the first term of the sequence is going to be the biggest. So when n is equal to 1, we get a 1 here. That's going to be an upper bound for our sequence. But we also realize that all of these terms are going to be positive. So 0 is a lower bound for our sequence. So now we have a bounded, monotonically decreasing sequence. Therefore, it must converge. And what does it converge to? If we examine it, we realize it does converge to 0. And with that, we will conclude our lesson on sequences.